Thank you for joining, everyone. We're going to be talking about our Halo Auto Test System, which allows you to automate performance verifications without using the traditional methods of testing a metal detector, which is passing test samples. Um, so the agenda for today, of course, we're going to talk about a little bit about Fortress. We'll go quickly through that, I promise. Then we'll talk about, why we test metal detectors, why we must test metal detectors. Of course, those are called performance verifications. So we'll talk about, um, the challenges when testing metal detectors, when we're talking about good practices when it comes to challenging metal detectors. Then we'll get into Halo, how metal detectors work, and so you can more understand how Halo operates and why ultimately it's a good quality of performance verification that actually improves the quality of the verification and adds a lot of value for our users. A little bit about Fortress. So what do we do here? We've historically been a manufacturer of metal detectors, but now in the last handful of years, we developed a dynamic weighing product with check weighers, and now X-ray systems. We serve all types of industries, food being the largest, consumer goods as well, pharmaceuticals, textiles, also other industries like plastics and lumber. We do a lot of different industrial applications as well, which is good. We learn a lot with everything we do, and we're able to bring it all back and share that knowledge and develop a better product. I'm located here in Toronto today. This is our head office. We also have three other global manufacturing facilities. So out of our four total facilities, we do manufacturing, sales, and service. Toronto is our biggest base, and it is where a lot of our R&D comes out of. So metal detectors. So why do we use metal detectors? Well, of course, to detect metal, because in most manufacturing facilities, metal is the most common contaminant that can get into the product. Of course, today with automation being more and more prevalent, it means less operators are on the line able to notice things. So the higher levels of automation, the risk of metal contamination actually increases. Food safety management plans, HACCP is a word that I'm sure that everyone's familiar with, which is hazard analysis, critical control points. So these form the basis of most food safety plans. And as part of these plans, you look for these critical control points, which are places where you can use some sort of inspection that can identify hazards and eliminate them or prevent them and reduce them to acceptable levels. HARPC, hazard analysis, risk-based preventative controls, kind of takes it a little bit further to identify specific hazards and apply control measures to those specific hazards to control them. So typically, a critical control point is going to be a metal detector. Starting to see X-ray systems become more and more popular. But again, the most common contaminant is metal. So unless you have other contaminants that X-ray is going to do much better at detecting, that you have risk of having in your product, in your process, then a metal detector should be the first choice. Two technologies I'm going to stress are not replacement technologies. Uh, they are complementary together. They'll catch a lot more. Um, let's move on though. Since the focus here is Halo and auto testing. So again, we have our critical control points, which are typically metal detectors in most cases. Now with metal detectors, part of your food safety plan, you'll have to state that how you test the metal detectors. Um, if you test the metal detector and it's not working, then all that food produced since the last good test is going to have to be considered unsafe. Corrective actions are going to have to be taken. So, there's no rules typically that state when you have to test. You have to have a plan that states your frequency and how it's tested and what you do should a test fail. Part of the test is always going to be documentation. That management system requires records to be kept for all the critical control points. So any work done, any verifications, and the results of those verifications. It states that if you don't have a result recorded, then you must treat it as if the test never happened. Yeah, testing is very important to ensure that your critical control point, your control measure, is effective and you can rely on it, and it means that it's working, that your product is safe. If it's not working, the product we've created or produced is unsafe. Again, the records are super important. Typically, these are handwritten, sitting on a clipboard somewhere near that critical control point. There's been a push in previous years, recent years, to automate record keeping and digitize it so that this cannot be messed up. So there are issues with record keeping, which we will get to. So when it comes to testing a metal detector and coming up with your performance verification test, there's some recommended best practices to make sure that your test is really going to be an effective evaluation of the system's performance. So of course, you've determined your critical limits, which are basically your test sample sizes that you're using on the system. And one thing you need to ensure is that you're testing those test samples in a position where it's most difficult to detect. Little picture on the top left, so those three positions in a metal detector aperture. The third position is the geometric center of the metal detector. This is going to be the hardest place to detect metal. Ultimately, this is where you should try and test the metal detector. That's going to produce the lowest signal from the contamination. So if you can detect it in position 3, you can detect it in position 2 and position 1, which are going to be closer to the coils and create a larger signal. The other thing, product testing. So you want to make sure that the test uses real and fresh products from the line. So typically you could take downstream of the metal detector, products that should be clean. You will insert metal into your product in a position where it's closest to the center of the aperture. And you're going to run that product through. The reason you do this is because product can have product effects, especially with food. You have moisture, you have all types of minerals. So these things affect the metal detector similar to the way metal does. So you must overcome this product effect before you detect metal. And typically, the residual product effect can add and subtract to the signals of the metal. So you might be able to detect metal on its own, but if you insert it onto the product, the signal produced by the metal may increase or decrease. And of course, the worry there is that you decrease it, or it's called masking, of that test sample signal with the product, and it can cause it not to detect that critical limit that you must be detecting. So it's important to use real product. The position along that product too is important, right? A performance verification, you must both test the metal detection, the detection capability, but usually it's part of a larger system, which is a conveyor with some sort of automatic reject. So you must also make sure that whatever contains the metal is not only detected, but rejected reliably. So it's good practice to test your metal test samples in multiple various pack positions along your package. Typically, this means the front of the package, the middle of the package, and the leading edge of the package, right? So that will cover the whether the product has any masking effect that affects the test sample signal. So fully testing the detectability of the critical limits. But it also allows you to determine if the reject is performing okay. You know, regardless of where the metal is in the package, if you had a kicker reject, for example, you want to make sure that that kicker is able to reject that product by kicking it at the midpoint along the length. And of course, that is effectively rejected. So these are the basic best practices. So again, aperture position, testing in the center of the aperture, put it in the product so that the product effect is considered as part of the performance verification. Different pack positions are tested, which will test the detection and the rejection. And of course, belt speeds and rates must simulate real product conditions. So typically, what you're going to have to do, especially on a higher speed line, stop the line, stage the product with samples that have contamination within them, restart the line, and ensure that the correct packs are detected and rejected. So again, this is fully testing the reject system of the metal detector system to ensure that the metal contamination signal is assigned to the correct package. With challenges when it comes to performance verification, there's different application-specific challenges. So these are the most common, which is conveyor systems. Typically, conveyor systems are your critical control point, or labeled as such because they are fully packaged products. So, you know, of course, to do a real good test of packaged products, the best practice would state that you take that clean pack downstream from the metal detector, insert the metal, and rerun that back through. Of course, once you do that, that clean and good, fully packaged product that you selected is now damaged, and you cannot reuse that and introduce it back onto the line without some rework at least. So in a lot of cases, what we see is packs being made up. So you'll take the product, you'll probably put some very visible markings on it so that it can't be confused with your regular production. And these packs will contain that reject or that test sample that needs to be rejected. Typically, they're used indefinitely until it becomes so damaged that it's spilling product out. So that's a bit of a problem because those test packs have the potential to be contaminated over time. You know, if you have contamination on that test pack, it might produce a signal that's detectable. So you might think you're detecting the test sample when you're really not. It might be detecting some larger piece of metal, some sliver, some flake that have somehow become attached to the pack. The other issue with these test packs is if we've had something, let's say a package of retail pack of flour, having that test sample in it, you know, you place it in a place where it should be going through that geometric center of aperture. But as that pack is handled and rejected, it becomes deformed. That test sample can move around to a point where it's actually much easier to detect, and it's not testing that worst case position in the aperture anymore. Gravity applications. So there's someone getting up on a ladder here, introducing a test sample into a gravity system. So typically, you know, gravity systems are somewhere in the process. Oftentimes they're not at a nice, you know, waist or chest height like conveyor systems are. Typically, they're up in the air in ductwork, mezzanine, ladders, sometimes scissor lifts are needed to access them for testing. So that's not only time consuming, but obviously there's some health and safety risks associated with testing of these systems. You know, working at heights, overreaching, straining, working in conditions that are often quite a bit hotter than packaging floors. So very difficult there in terms of being an operator testing these applications. We also have, you know, simulating the real production speeds means introducing your test fall or test sample at the free fall height of the product. Unfortunately, a lot of times people want to test the metal detector at the metal detector, not somewhere upstream, which makes sense. You want to maintain sight of your test sample if at all possible. What we see here in this example, we have 3 gravity systems. So a scanning pipe with a metal detector around it, and below it we have a reject valve, which will reject small handfuls of product containing contamination. Just above our black scanning pipe, we have the metal pipe that's feeding the product to a metal detector. And you see there is a test ball insertion port. So the problem here is again, the speed that your test ball is going to be traveling at. That test ball is going to be slower, inserting it slower as it moves through the system, inserting it just above the metal detector than it would if you had inserted it at the free fall height. In this case, just above the bend of the pipes are probably a much better place to be inserting the test sample. So again, testing these is notoriously difficult, usually due to access, sometimes due to the desire to be testing them at metal detector height. The other thing with these systems is the trajectory that test ball is going to take. You know, whether it's introduced properly even further upstream or inserted in a test ball insertion port, more than likely that test ball is not going to fall through the geometric center of the metal detector aperture. It's going to be bouncing around. So to really get the worst case test, you probably have to test it many times over. Hope that one of those times you actually get it falling through that geometric center of the aperture. But you know, it's really nearly impossible to run that test in the center of the aperture unless you can actually break the line, position that test ball in the center of the pipe, and then drop it there at the free fall height of the product. Another very difficult to test properly application is the vertex or float application. This is typically a slimline metal detector placed over a bagger and underneath a multi-head weigh scale. So in this, typically to test this, you have test balls or test cards that would be dropped at the scale above. Now you can see here is there's a funnel, a plastic funnel that's actually sitting between the scale and the metal detector. And the test sample is going to be traveling along this scale tip or this plastic funnel, which again, it's going to direct it towards the sides of the scanning pipe, not in the geometric center of the metal detector. So we're not testing it in the worst case position. More often than not, we're going to be in the easiest to detect position when testing with metal detectors. Also, when you think about how this is tested, if one person is testing it, they're going to have to go up all the way to the mezzanine where the scale is located. They're going to have to drop that test sample through there. And then they're going to have to go down, make sure the metal detector detected it, going to make sure that the signal that was sent out by the metal detector alarms the bagger. Typically, the bagger was going to stop or it's going to create a very long bag. During all this, typically the line is also stopped so that you reduce any risk of that bag going out containing a test sample. These baggers are working at pretty high rates. So if you fail to detect for whatever reason, it's going to be fairly time consuming and difficult to figure out where that test sample is. So we're also probably not testing with real products. So time consuming, not testing with real products, not testing center of aperture. And again, there's a real problem here is how time consuming it is. It can be very costly. Oftentimes, two people are required to test this, one person above to drop the sample, another person below to monitor it and make sure that it's detected and rejected. Snack food plants usually have more than a few lines. They might have 20, 30, 40 of these systems. So we can see it may quickly become a full-time job for someone just going around testing these metal detectors. Another notoriously difficult test system, usually the performance verifications are very flawed in their design due to the challenges with properly testing these. There's a pipeline, so generally liquids, slurries, meats, pastes are pumped through a pipeline, detected by a metal detector, and favorite reject on these is a ball valve, which is used to redirect the product downward into a reject bin. So inline tests on these can be time consuming to perform and almost surely they'll be very messy. Messy means you're also wasting some product. So typically what you want to do on these systems is use a test ball insertion port, which you're able to then upstream of the metal detector get a test sample into the pipe. And then you're going to run that sample through the system, make sure that it rejects. That's a good test. That's going to be a bit time consuming. Sometimes the parts are inserted on the line only for the test. So pulling the line apart creates a mess with the product. And again, the reject, should it not reject, will also have another section of pipe downstream of the system, which will catch that test sample. Again, typically you have to insert that for testing and remove it when you're not testing the system. So yeah, very messy, very time consuming, which usually leads us to a situation where a test is developed for the metal detector of verification that does not follow best practices. So this is what a test typically looks like on this type of application. You have a test wand, you insert it between the scanning pipe and the metal detector aperture. You look for the product to reject and the reject signal from the metal. Of course, this is not the worst case scenario. It's not testing the center of aperture. Reject timing is also fairly questionable. But, again, this is due to the fact that testing is I suppose, deemed unfeasible due to the time and waste and the mess that it creates. A lot of other challenges with performance verification, or at least manual performance verification. Record keeping is one. It's necessary when testing, but can be overlooked. They can be falsified. They can be lost. They can be damaged. They can be hard to read sometimes. I know my writing is progressively gotten worse over the years since we do a lot more typing these days. Human error, that could be with the record keeping. It could be with the test, with placing the sample. People are not perfect. They do things differently, sometimes understand instructions differently. And unless we're really watching, we might not catch the human error that's introduced. Of course, humans, they're under a lot of pressure sometimes in these production environments, getting through things quickly, making sure the line's not down too long. are they're trying to make everyone happy, not only quality but also production. Um, Sometimes the interests of those two parties do not always align. I hope it doesn't happen often, but falsification of test records is completely possible. In performing performance verifications for test samples can be a problem. One, they can become further contaminated too, or adulterated. But you're also having to introduce them into your product flow, your good product flow. So there's always that that off chance that the test sample gets lost during testing, it doesn't get detected, doesn't get rejected, and becomes lost in your product and becomes your foreign matter within the product. Of course, with all testing, there's labor associated. There's also sometimes downtime, which means that you're not producing stuff. If you're not producing products, you're not making money, so there's lost profits, which are part of the cost of testing. So Halo, what is it? So it's an automated testing system that will perform your metal detector performance verifications without the need to introduce metal, without the need for operators. It can be completely automated, or there can be some level of operator intervention, but it's able to perform these verifications, improving the quality of the verification and reducing most of the cost, while also overcoming many of the challenges that we've spoken about. So just a little background on auto testing. It's not a new notion. Um, as long as metal detectors have been used in food and consumer goods manufacturing, there's always been some attempt to automate testing on metal detectors. I'll say that until Halo, I haven't seen anything as sophisticated and reliable and really nearly as awesome. So back in the 70s, typically this detector generated pulse means that there's a disturbance made in the electronics of the metal detector. It's not calibrated to metal samples. It's not creating the same phase of the metal. It's not really simulating or replicating the metal test at all. It's just creating some sort of disturbance that is then creating a reject event. So it was never widely adopted because it was never a great performance test for the metal detection. Sure, it worked good enough for the rejection portion of it, but it was never replicated in the actual metal that was detected. Another system there that's quite old, I still see it very sparsely used today, usually maybe not used, but at least installed in some places, is a system that's very mechanical, where little test samples, so small ball bearings of hopefully calibrate sizes, are shot through an airline using air. Now, it's a little bit better, I suppose, as you are testing real metal. It is checking and inspecting the disturbance caused in the field, but it doesn't follow a lot of the good practices. Of course, you're going in the corner of the aperture opening usually, which produces quite a larger signal than if the metal was passed through the center of the aperture. And just the mechanical nature of it becomes has a lot of inconsistencies into the quality of that test. The speed may be affected by friction, it may be affected by air, it may be affected by just changes in the way that airline is positioned through that aperture. So it was never, again, a test that was widely adopted. Around 2012, we did other work, not so much auto testing, but improving the performance and manual verification to try and reduce some human error and potential cheating of the test. So this utilized a test sample folder with coded test samples so that we monitor that they are in a position or in the folder at all times unless they're being tested. In that case, you're only allowed to remove one at a time, and they can only leave the test sample holder for a specified amount of time before they set down the line and create a fault. So it's a little bit better control on top of a manual test, but still not an auto test. In 2014 or thereabouts, we developed Halo for the Vertex application. We saw some big concerns with vacuum manufacturing, generally due to the cost of testing and the increased frequency of testing and the importance of you know, having critical control points became much more important. So we developed Halo for those lines and since adopted it to all types of different metal detector applications. So the Halo performance verification, it's a true test. There's no connection to the actual metal detector when it comes to making the test. It creates a disturbance in the electromagnetic field that is indistinguishable from actual metal traveling through the metal detector. We calibrate Halo on the metal detector that we install it on using the calibrated test sample so that we end up with a signal from the metal detector perspective that is exactly identical to this disturbance in that electromagnetic field that the real metal test samples would make going through the geometric center of the aperture. So it tests the worst case and is calibrated to known sizes and types of metal. So with any metal detector, we're looking at a few different properties, the conductive and the magnetic properties of any signal disturbance. So Halo is able to replicate both of these, which is we represent as a phase. Okay, so ferrous metal is magnetic and quite a good conductor. So it has, but typically the way that the system's set up, you get a higher X signal with phase opposed to a 90-degree axis. Stainless steel, we use non-magnetic stainless steel as a metal detector test because it's the worst case, it's non-magnetic and typically a poor conductor. This phase is along the 0-degree axis or thereabouts, depending on the size. And then the third class of metal that we have is in non-ferrous metal. Pretty good amounts of both conductive and magnetic properties. It's not attracted to a magnet, but it does create that magnetic signal. And that phase is somewhere in the middle of 45 degrees. So with our Halo test, we calibrate it to those test samples, and we're able to replicate both of these types of disturbances in the electromagnetic field. So we are exactly mimicking the type and the size of the metal. So that ratio of your RNX signal relates to the phase or the type of metal. And then we scale those ratios up and down to get the resulting peak signal on the metal detector as which will then replicate the exact size sphere when it comes to that disturbance in the electromagnetic field. So we have the type of metal, which will react to changes of phase the same way real metal would. We are getting the same peak signal generated, which determines the size. And then we also change the frequency of the signal depending on the speed that the conveyor or gravity system will need to inspect that. So Halo essentially gets a belt speed reading from the metal detector to adjust the frequency. So these three things means that we're exactly mimicking or exactly replicating the signal disturbance of metal, following best practices, um, real rates, real speeds, um, real phase, and to the metal detector, it doesn't know what or where that signal disturbance came from. It only knows that there was one. So the metal detector, the signal created is indistinguishable from real metal running through the geometric center of the aperture, um, replicating both the size and type for your ferrous, non-ferrous, and stainless steel test standards. The results, well, when you're using electronics to create this signal disturbance, it's going to be a lot more repeatable than doing a manual test. You can try every time to get that test sample right in the center of the aperture, but there's always going to be a level of variation with the manual testing, with trying to introduce this test sample and trying to do it fairly quick. The top waveform you see, that is a signal that we generate from the halo sample. As you can see, it's accurate, it's precise, it's the same every time. Below is what we'll see when you're doing manual testing. And the bigger the aperture, the more pronounced that effect is going to be. So again, it produces a better controlled test, which is more able to simulate that worst case scenario center of aperture time and time again compared to manual testing. The other thing is we run the Halo test along with real product going through. So with the feedback from an in-feed photo eye on the metal detector, we are able to inject that Halo test sample into the product along any edge of that product or any position within the product. So ultimately, what we're trying to do is replicate that test where that good practice where you must run with real product because the product signal or that product effect can cause the variation in the test sample detection signal. So it can add or subtract to it. And Halo, again, because it's creating that disturbance in the aperture while the product is going through, it will do just that. So you get the same result placing the test sample into the product as you would injecting that replicated test sample by Halo into that product. Again, Halo is also capable of performing multiple tests with each metal, and it uses the feedback from the metal detector photo eye to determine where that pack is and determine the exact time to inject that replicated disturbance or replicated test sample onto the package that's traveling through the metal detector. So not only will it test the detection capability when it comes to product effect and product masking, but it will also be able to test that front, middle, and back of the pack to ensure that the reject system is also able to accurately reject that package where it needs to. So how does Halo work? Well, let's first talk about metal detectors. So metal detector is basically comprised of a few coils. So in the center of the metal detector, we typically have a coil there, which is a transmit coil. This is a coil that we're driving current through that so we create this electromagnetic field that fills the body of the metal detector and actually kind of leaks out of the sides of it as well. Also in the metal detector case, equally spaced around the transmit coil, we have a receiving coil. So essentially what's happening is we're inducing current flow in the receiving coil on either side of the metal detector. Now that receiving coil is wrapped twice around the metal detector, once on either side, and it crosses over at the center point to wrap back in opposition to itself. So what happens is on one side, you're driving current in one direction. On the other side, you're driving current in the equal amount of current in the opposite direction, which results in theory of a net voltage across that receiving coil of 0 volts. So now we're looking at the voltage produced on the receiving coil, and we're looking for changes. Typically, what you see is a sine wave with changes of amplitude and changes in phase, dependent on what type of signal disturbance is created in that electromagnetic field. Right? So you'll get a slightly different combination of that phase and phase shift and amplitude change, depending if your contamination or product is more or less conductive or magnetic. So we look at those two properties. We kind of do some signal processing, so we end up with our R signal and our X signal for your conductive and your magnetic signal. And what we do is we look for either one of those to increase too much or too fast, and that essentially tells us that we have metal moving through the aperture, or a signal disturbance that's large enough that we call a detector. So the metal detector, it's not looking for metal specifically, it's looking for a disturbance that metal creates. So things that affect your performance on a metal detector. One is the product that you're inspecting metal within. Of course, food and a lot of, maybe not so much with other consumer goods, but with food especially, there's a lot of conductive food out there, high moisture, there's minerals. So food can be difficult at times to detect metal in, because it's affecting that electromagnetic field the same as the same way the metal does. Because methods to overcome that product effect and still get pretty good results. So the orientation of metal also affects a metal detector, right? We use test spheres because they don't have any product effect, but there's orientation effect with especially pronounced when it comes to long, thin types of metal, like wires, needles, things of that nature, where in one orientation, they may produce a very high signal so that you think they couldn't be missed. But in the other orientation, they can create a very low signal. And again, this is all due to the way that it passes through the electromagnetic field and the level of disturbance that it causes as it passes through. Position in the aperture, we've also already mentioned that the position of that the metal passes through is going to affect the signal produced. Of course, the center is the weakest point. Type of metal, so all metal is not the same, right? They generally are classed into 3 different categories. You have ferrous, so those metals that are attracted to a magnet. Those are typically the easiest to detect due to the highly conductive nature of them, and they also have that magnetic property that's quite profound. You have your non-ferrous metals, so your aluminum, your copper, your brass. These are very good conductors, but are not attracted to magnets. So depending on what mode the metal detector is running in, they're as easy to detect or slightly more difficult to detect than the ferrous metal. Third type of metal, very important, is your non-magnetic stainless steel. Stainless steel is probably the one of the more common materials of construction you see in plant equipment. And it is also, unfortunately, the most difficult type of metal contaminant to detect. It's, of course, you use non-magnetic stainless steel because it is the worst case and hardest to detect thing. Stainless steel that can be attracted to a magnet. But stainless steel in general is not a great conductor compared to other metals. So it's always going to be the most difficult contaminant to detect. Other things that can affect the metal detector performance are with the installation generally. So metal moving around the metal detector can create a disturbance in the field that can cause detection. Um, Metal detectors are also working essentially radio frequency transmitters and receivers. So there's potential that other equipment in the plant uh, have the potential to create RF interference at a metal detector can see. Typically, this is motor drive, so variable frequency drive can create harmonics of their operating frequencies, which can radiate back onto the line and over the air. Earth loop. So this is one that's very important because it is kind of the what Halo is based on, which can be found in conveyor frames or surrounding framework around a metal detector. And essentially what it is a loop that current can flow in, um, which has some intermittent connection. So we'll provide an example here. I'll show you about a ground loop, how it looks and what it does to a metal detector. So in this next clip here, I have a wire. We place it in the metal-free area of the metal detector. We show that it's not creating a signal just sitting there. But when we close the loop, so I have a wire right here. When we close the loop, current starts flowing in this conductor, which then an electromagnetic field expands around the conductor. And this all creates a disturbance in the metal detector field, causing a detection. Same happens when we break the loop. That electromagnetic field collapses, creating a change that the metal detector will then see as a detection. So here I'm closing the loop, seeing detections occur. And now I'm waving it in front of the metal detector. You can see that, it's not the metal of the wire creating that disturbance. It's not seeing the metal in the metal-free area. It's indeed seeing that loop. So that's pretty well what Halo is, okay? It's a loop that we control using electronics. So the theory is, a very high level basic theory, is that we can take these loops and if we can control the current passing through the loops, we can control the disturbance that we cause in the electromagnetic field. So Halo essentially is set up. There's another processor on the Halo electronics completely separate from the metal detectors. That combined with other passive components, so resistors and capacitors, we can control the amount of current and the phase with respect to the metal detector and exactly mimic the disturbance that real metal would cause moving through it. And we can calibrate this to specific sizes and types of metal traveling through the center of the metal detector at line speed. So it does this, again, there's a processor in there, there's some passive components, and it does some fancy switching to exactly look like metal passing through the metal detector to the metal detector. There is a convenient connection that exists between the Halo system and the metal detector, but the disturbance caused to the metal detector, that the metal detector sees, is always completely over the air, completely isolated from the electronics. Essentially, there's an HMI there on the metal detector. So out of convenience, there is a connection there to the Halo board to tell it when to perform the test. And also, it assists in the data logging of the Halo test. So the metal detector knows that, hey, I need a Halo test. The Halo test fires that test. And if the metal detector doesn't get the signal, it fails the test. If it sees the signal, it passes the test and logs it as so. So yeah, there is a connection there completely out of convenience. We have the HMI, we want to log it all on metal detector log. And there's some settings that are shared that Halo will read, such as the felt speed or the state of the in-feed eye on the metal detector. But there's no reason why we couldn't control it in another way to have absolutely no wiring connection at all to the metal detector. Of course, the complicates things when it comes to logging that test through the metal detector log, because it would not be the metal detector requesting the test, so the test would be requested by a laptop or PLC. But the point is that it is a completely separate kit from the metal detector itself. The metal detector is in no way testing itself. Reject verification. So Halo creates a disturbance that tests the detection performance of the metal detector. Now, the metal detector has its own way to monitor the reject, right? We fit it with various sensors that look for product going into the bin, that look for product coming off the end of the conveyor, that says whether the bin is full. So these are all considered as part of the Halo test. So essentially, you'll have confirmed sensors. They should be set up on the metal detector, and you create a reject confirmed time. So a minimum time that it must be that package rejected. Otherwise, you consider that a failed rejection. This product is probably passed. So if the metal detector doesn't think it rejected product properly, may it be from the looking at product going into the reject bin or checking what products are coming off the end of the conveyor, it will create a fault. So if a fault condition happens during a Halo test, Halo will fail that test. The system will go into fault, and it will be logged as so on the internal log of the system. So again, this is just showing the various sensors that we can have. So E is our reject confirmed sensor, the product going off the there in the bin. Sensor C is an exit sensor. This metal detector that knows what should be leaving the conveyor based on what's coming on and what should be rejected. So if there's product that appears there that should not be there, it will fall. Product disappears that should be there, it's also going to fall just off the line. We have an automated reject device. You can also put sensors on the reject device, monitoring the state of the reject. F is pointing out the in-feed sensor, so it's always a good idea to detector system with that in-feed sensor that will allow it to register product coming onto the system and track it all the way through. Without the metal detector in-feed photo sensor, the metal detector is only looking at the electromagnetic field and any disturbances. It doesn't know where the packages are, and depending on the reject device, it may struggle with actual rejection. Reject verification can be also applied to your gravity system, to your pipeline system. Typically, proc sensor or mechanical switch will send a signal once we confirm that the reject is in the reject state. Again, we can validate those settings fully with failure, so we know what the minimum confirmed time is to be, so that we can rely on that as part of the Halo test to do that. Test the reject verification. So Halo, it can also eliminate tampering with product. Of course, because it's using clean product going through, it's eliminating operator intervention for the most part. It's injection that has samples. Settings are not editable by the end user. Those are set up by Fortress at our factory. It's not the case. So there's no test samples in there. There's no extra opportunity to introduce more metal into the pack that you run the test to have all on live. Automated records, I mentioned this a number of times. With examples here of a log event on an L detector. So this can be used in place of your metal detector performance verification logs. It logs what operator has performed the test. It logs the test time, and it will log whether it's pass test or a failed further to this, there's also greatly helping the investigation since it logs all detector events. It definitely logs all Regis events, all faults, all configuration changes, um, all tests, whether they're Android or Halo verifications, and all of these events are also linked to settings at that time that they on that product that's running. So Halo, of course, overcomes a great deal of the safety concerns that we have when that are associated with testing metal detectors, right? Halo can pick up mostly the performance verification, um, optimum experience, performance verification. I feel like some very loose frequencies. Halo do the rest, so take operators away from those uh, working at height for the most part, and those remove them from any hazard presence. So we completely um, Halo also provides payback. Does it's reducing the cost associated with having posting labor, and also it doesn't require you to off the line of the product. So so go over a few of these costs. I'm running out of time here. So almost to the end. So a few different examples here. So this example is the cost savings. Okay, so this is on one line that is a detector installed on. We're making an assumption that we're only 12 performance verifications per day. We're going to assume that it takes 5 minutes of labor time to perform tasks, and this is just going down to the machine, performing the test, boarding the test, restarting the line, leaving line task, and we'll assume that this is a quality in that's performing the test at their hourly rate, $50 an hour. So this works out to $50 a day, $1,520 per month, $18,250 per year. So this is on one line of it. See that the Halo has a fairly quick return on investment. They're paying stuff off in a loan, whereas around a few months. So we see below the savings. We're assuming that Halo is doing 11 of the 12 tests, so it saves $45 a day, $13.94 for 15,000 a year. Now, this is more attractive once we get to the cost stage with downtime, right? So the product is not being produced. In this example, we're assuming that each product that we're producing has 20 cents profit. We're going to assume a moderate production rate of 50 packs per minute, and we're going to call it 3 minutes of downtime per pack. So you can see the cost of testing quite a bit greater than just the labor portion, which also applies not to the calculation. So $290 per day, $8,800 per month, 105,000 per year for Halo. And we are going to do all those ones after Halo. So perform the ones that release. It's going to save $265K, over $8,000 per month. Just shy of $100,000 over the year. So, in this example, Halo does not only pay for itself very quickly, but the whole sector system it's probably paid for well under the picture as well. So the last thing we're going to talk about auto test systems are becoming popular. So it's going to be a bigger push for the test system. We need to talk about what creates a reliable auto test system, something that's really going to replicate performance verification with good quality tests. So again, one, it must be calibratable, known test sample sizes, types, also replicate speed. Okay, so again, that's what Halo does. We calibrate it to NIST traceable test samples. It must create that signal disturbance in the reference field. It has to be separate from the electronics. It must be creating that signal disturbance same way that the tester is looking for that metal. It should, again, not only replicate the metal, but replicate the center of atmosphere test for that weird case. You have to be able to fully balance the reject device between the form of front and the middle and back of the cycle test. So that we're fully testing just the product of that produced as well, but it also makes sure that the other testing is right. It should automate the record if this goes without saying. Records are very important. Because the records are very susceptible to tampering and dog. So automating digitizing test samples or test verification test records is very valuable. If you look at it second spring, it will be accurate. Exactly what. Again, Halo creating the security code the parent. It's a completely separate device. Rules are the handshake between it. So essentially, the auto test systems cannot be software, cannot be a feature of the metal detector itself. It can be completely separate. You don't want a metal detector that can itself. They must be tested by the the other thing, you must make sure that the test itself provides a test that improves quality. So Halo does that. It's able to replicate that method reliably in those applications that is very difficult to get to that to apply the best practices. It overcomes all of those challenges. So again, something separate, do the testing, exactly replicate those signal disturbances, calibrate it, test those sizes, types. I went a little bit over time, but I'd like to thank everyone for joining me. I'd love to thank Canadian Packaging for hosting this. Thank you all.